All right, class, let's explore changing medium. Let's specifically look at how a changing medium will affect the speed and wavelength of a wave. So let's start with an example problem here. What will happen to the wavelength of a sound wave that originates in water and moves into the air? So here we have at the bottom of the ocean, the mythical beast Cthulhu down there in the depths, and he vibrates his tentacly vocal cords and makes a tone, a sound. And that sound travels from the water into the air. From the water and into the air. And let's draw like a little waveform with its crest, trough, crest, trough, crest, trough, crest, trough, crest, trough, and we'll stop there at the boundary. And what this question is asking about is what will happen to the wavelength. What will happen to the wavelength? There's that symbol for wavelength, meaning the distance from crest to crest, that wavelength. So what's going to happen? Let's consider some other variables. The wave source determines the frequency. What's the wave source in this example? That's Cthulhu. He or she is the wave source. So he's going to determine the frequency by how fast or slow he vibrates his tentacly vocal cords. So he determines the frequency. The medium determines the wave speed. So whether or not we're in water or in air, that's what the speed of sound is dependent on. The wavelength is a dependent variable. What that means is that the wavelength, this is the effect in this example. This is something that you cannot directly change yourself. You have to tinker with the frequency or the wave speed in order to indirectly affect the wavelength. It is the dependent variable. So let's write the wave equation down. That's going to help us out. That's going to give us everything we need to solve this problem. Wavelength is directly proportional to the wave speed and inversely proportional to the frequency. Wavelength equals velocity divided by frequency. Let's just write in those relationships. Velocity here, wave speed, is in the numerator. So if that increases, wavelength will increase. That's a direct relationship. You've seen this before, very helpful model. Frequencies in the denominator, there's an inverse relationship here. That's an inverse. If frequency doubles, wavelength will halve, or frequency increases, wavelength will decrease. And let's also write in that the wave speed, that's determined by the medium, and the frequency, that's determined by the source. That's the source. And look at all this. There's a lot of information here. This is a nice, important mathematical model that shows these relationships. And it also is labeled a little bit that helps us figure out, what is influencing what. Okay. Last thing that we need here. We need these two facts, #facts. The speed of sound in air is about 343 meters per second, and the speed of sound in water is about 1,480 meters per second. This is helpful to me because I now know that the speed of sound in air has a small velocity and the speed of sound in water has a big velocity. So let's add the V symbol, velocity, to my little model up here. So we have a fast velocity in water, we have a slow velocity in air. That wave will slow down when it encounters this boundary. That wave is going to slow down. So what's the effect on the wavelength? Let's draw the wave equation one more time. Wavelength equals wave speed divided by the frequency. Does it say in the prompt, does it say that Cthulhu modulates the tone of his sound or that he sings at a higher and lower pitch? No, it does not say anything about frequency changing. Frequency is constant in this example. I'm going to draw a lock on there. That's locked. Frequency does not change. The velocity, the wave speed, that does change. It decreases when the sound goes from water to air. And so if the velocity decreases, then the wavelength also decreases because of the direct relationship between velocity and wavelength. Real simple. If velocity decreases, so does wavelength. So we have the answer to our problem here. We have our answer. What happens to the wavelength? It will decrease. It will decrease. And let's just draw it in here. Add the waveform to our model. So here we have the longer wavelength, and then we're going to have shorter wavelengths here. Try not to make those too zigzaggy. Anyways, you get the idea. We have shorter wavelengths when the sound crosses from water into air. Let's write it down. Text box. Yeah, the wavelength will decrease because the medium changes from water to air. Sound moves slower through air, and wave speed and wave length are directly related. Directly related according to the wave equation. Look at that. A claim with evidence and reasoning. That's a great answer right there. Make sure to write that down on yours. Okay, just a couple other things we'll scream through. Things that don't affect the wave speed, the amplitude does not affect the wave speed. We have, say you are at a football field, you say blue 42 set height. That sound wave is going to travel down the length of the football field. It's got a certain velocity. Say you want that wave to travel faster, so you do an experiment, you yell louder, blue 42 set height, you yell a little bit louder. Well, guess what? Those two waves, they're going to have the same velocity. I put a lock on there. Velocity is constant. Amplitude does not affect the speed. You're not going to get that wave to go any faster. So let's look at frequency here. Ba-doop. Come on now. Here we go. So in this little GIF, whatever you call it, we have a low frequency wave up at the top here, low frequency, and a high frequency wave being generated in this demo on the bottom. And if you track these wave crests and you look at how fast they're moving, you'll notice they've got the same speed. They have the same velocity. The increasing the frequency is not going to affect the wave speed. That's what changing the medium does. So looking at a couple examples of a changing medium, a sound wave moving from cool air to hot air. Temperature affects the air particles, and that's going to affect how the sound travels through them. So we got about 343 meters per second. That's how fast sound travels through like room temperature or just regular, nice day. If you're really hot in the desert, it's going to travel faster. That's just how it works with sound. There they are at the North Pole. It's a lot colder, so the sound is going to travel slower. I don't know if those numbers are accurate, but you get the idea. So the temperature affects the air molecules, and so you get a faster or slower sound wave through those mediums. Look at this, a transverse wave moving from a thin string to a thick string. So we have maybe a fast-moving wave going down this thin string, but when it hits this boundary here, this medium boundary, the wave's going to slow down. Why? That's a thicker rope or a thicker string. It's got more molecule. It's got more mass, so it takes more energy to move it. It's got more inertia, so yeah, that wave is going to slow down so that energy can be conserved. A seismic wave moving through layers of the earth. Seismic. That's an earthquake wave. So what happens when this seismic wave goes from different sedimentary layers to maybe a denser sedimentary layer? It increases the speed. The earthquake starts to go faster because of the difference in medium. Also notice with these arrows, the earthquake wave also bends. That's another thing. Whenever you have a changing medium, you have something called refraction. And the classic example of that is the prism. This is a light wave moving from air into glass. And what happens to these waves? Well, it just so happens that the waves bend. The blue and purple waves, they bend a little bit more. than the red waves, and so that white light gets separated into its different colors. That's just another phenomenon that we see. Kind of cool. So changing medium bends the wave. Check this out. So we got this wave on this little demonstration, and the wave crosses that little medium boundary there, and notice how much faster the wave goes. Look how much faster the wave goes when it hits that second medium. Notice this other phenomenon that happens too. Right here, you can see a reflection. So anytime a wave, think about a light wave hitting a glass mirror or something, the wave, part of the wave actually reflects back. That's why we get reflections, is that changing medium. So changing medium does a lot of things, but most importantly, it affects the wave speed, which will affect the wavelength. There you